Chapter 17 focus around acids and bases. This is a very important subject in all branches of chemistry, and it's something that you sort of end up studying a little bit in each of your chemistry courses and kind of build off of it. So even after this, you'll go on to organic chemistry and you'll revisit the subject and build off of what we learned here today. Okay? So let's start with some definitions here. What is an acid? What is a base? Okay? So these would be considered the Bronsted-Lowry definitions of an acid and base, named after these two researchers. And this is the definition that I find most useful. Okay? An acid is defined as a hydrogen ion donor, something that loses a hydrogen ion in a reaction. Okay? Now, let's think real quick. Hydrogen ion, if we look on our periodic table, hydrogen is element 1, right? So I'm holding a hydrogen atom in my hand. How many protons am I holding? 1, right? Because it's element 1. That's what it means. That's what the atomic number means. Okay? Cool. So if this hydrogen atom is neutral and I have this 1 proton, how many electrons am I holding? It's not a trick question. I need my electron to counterbalance my proton, right? So I have 1 electron as well. Okay? So now I'm going to create my hydrogen ion by removing that electron. What am I left with in my hand? Just a proton. So these hydrogen ions, we call them protons. So we would say that an acid is a proton donor, right? And again, by proton, I really mean that hydrogen ion. All right, so what is the base? The role of the base is the exact opposite. It's going to be the thing that accepts that proton. The acid gives it up, the base takes it. All right, so our base is a hydrogen ion acceptor. And again, we would call that a proton. So a base is a proton acceptor. Cool. All right, so let's take a look at an acid-base reaction. Something that you would have used these chemicals in general chemistry before. We're going to use HCl, hydrochloric acid, and hydroxide, a very good base that's very cheap and commonly used in the lab. Okay? So in this reaction, what's playing the role of the acid is hydrochloric acid. Got it in the name, right? And my base is that hydroxide ion. So if I'm going to draw my products of this reaction here, my acid has to lose that proton, right? That's what acids do. They give up their protons. So what I'm left with is just that chlorine. All right, but because it gave up a positively charged hydrogen ion, it's also going to be left with a negative charge. So I have a chloride ion as one of my products. My base does the exact opposite. It accepts that hydrogen, right? So now I have 2 hydrogens in my formula. And likewise, it accepted that positively charged hydrogen, so its charge is going to go up, and now it's neutral. Okay? So this would be my products of this acid-base reaction here. Right? Again, you just want to convince yourself that you can see that my acid is losing the hydrogen, and my base is accepting that hydrogen. That's what we're going to see over and over again in our acid-base reactions. All right? We have fancy names for the products here. My acid, when it loses its proton, it becomes the conjugate base. When my base accepts the proton, it becomes the conjugate acid. All right, so again, my acid becomes my conjugate base, and my base becomes my conjugate acid. All right, So why? Where does that, like, why does the acid become the conjugate base? Why does that work, right? Well, remember, we got to update our way of looking at chemical reactions here. Now that we're in Chem 1B, we don't just look at them as going one direction. We look at them as going in both directions. And if we look at the reverse reaction, what's playing the role of the acid is my conjugate acid, right? What's giving up a proton is my conjugate acid. And in the reverse direction, what's playing the role of the base, what's accepting the proton, is my conjugate base. So that's where this terminology comes from here. We have our acid turning into our conjugate base, and our base turning into our conjugate acid. Okay? Cool. So I'm going to give you another acid-base reaction here, and you're going to label what my acid is, what my base is, what my conjugate acid is, and what my conjugate base is. All right? So ammonia, and this thing here, what's called acetic acid. They react to form an ammonium ion and what's called acetate. All right, so you're going to label my conjugate acid, my conjugate base, well, my acid, my base, my conjugate acid, my conjugate base. All right, what's donating the proton? What's accepting the proton? All right, so the NH3, what is that? That's our base. You will see nitrogen playing the role of a base quite often. It's a very common base, especially in organic chemistry. All right, I called this thing acetic acid. I guess I kind of gave it away. That's our acid. Do you have to know the name of it? No. Do you have to be sort of comfortable with me standing up here saying sciencey sounding words? Yes, right? We don't have to memorize the name and formula of everything that we hear, but we need to get comfortable with that kind of stuff, right? We're going to see a lot of formulas. We're going to hear a lot of sciencey sounding names. All right, so then what does that make my ammonium ion, my NH4+? My conjugate acid, right? The base becomes the conjugate acid. And my acid becomes my conjugate base. All right, cool. What's up?
So with the reaction, is it always going to be the ones on the left always going to be base and acid?
No, right? I actually switched them up from what we saw above. There's no order in which things have to appear in your chemical equation. Kind of like A plus B is the same thing as B plus A.
And I know, like, so the conjugate, both of the conjugates don't have to be on the right; they can both be on the left.
Oh no! Of your chemical equation, when you have your arrows, acids and bases are your reactants. Conjugates are always your products. Yes. Okay, so we want to be able to predict the products here, right? I gave you what these products are. We want to be able to draw them ourselves. If I give you an acid, what is its conjugate base? If I give you a base, what is its conjugate acid? All right, we would call these the conjugate pairs. Okay, so again, given an acid, what is the formula for that conjugate base? All right, we got to apply the same logic each time that we do this here. So let's just take a look back at one of the ones that we covered at the very beginning. All right, so we're going to make a little table here. That very first example that we did, was with hydrochloric acid, and that became a chloride ion. All right, so how do I go from my formula for my acid to my formula for my conjugate base? What happened to the number of hydrogens? Did it go up or down? Down, right? So I'm going to decrease my number of hydrogens by 1. And then what happened to the charge? I went from being neutral to having a negative charge. So I'm also going to decrease my charge by 1. All right, that's the logic that we've got to apply. If we're given the formula for an acid, we can figure out what its conjugate base is by decreasing the number of hydrogens by 1 and taking that charge down by 1. All right, so I'm going to put up some acids, and you all are going to give me the conjugate bases. All right, so to get my conjugate base, I'm going to decrease my number of hydrogens by 1. So now I have H2PO4. And I'm going to take my charge down to -1 as well. Okay. You will see, and I have absolutely no rhyme or reason. Sometimes I write my -1 charges with just the minus sign. Sometimes -1. You'll also see in chemistry 1 with the sign on the other side. That drives me nuts just because I was kind of a math physics-y background guy. But anyways, you will see that a lot. All of those are equally correct, okay? All right, so now I have my HSO4. I'm going to take my number of hydrogens down by 1. And now my charge is already -1, so I have to take it down to -2. Okay. And now we have water. Again, we're going to take away a hydrogen and decrease the charge by 1. Okay? So, real quick, looking at this thing here, importantly, this guy has a very special name. It plays an important role in acid-base chemistry. This is what we call a hydroxide ion. You will also see it written as OH minus. The negative charge is technically on the oxygen, so I like writing it the other way, but you will see it in this shorthand as well. Okay, but this is going to play a very important role, so we got a fancy name for it. This is a hydroxide ion. Okay, the other thing that I kind of want to point out here is there are compounds that we think about as acids. The name of this right here is hydrochloric acid. It's built into the name, right? We also have water here in our acids list as well. Water is not something that we think about as an acid. If we spill water on ourselves, what are we going to do? Go rinse it off with more water? We're fine, right? So, importantly, when we're talking about acid and base chemistry, we're talking about these roles of a proton donor and a proton acceptor. Yes, there is a class of chemicals that we consider to be acids because they very commonly play the role of acids. But when we're looking at an acid-base reaction, anything that donates a proton is the acid in that reaction. Anything that accepts a proton is the base in that reaction. So water can very much so play the role of a proton donor, even though it's not something that we would classify in our stockroom as an acid. Okay? So again, when we're talking about acid-base reactions, we're talking about these roles of proton donor and proton acceptor. All right, so now we want to go the other way here. If I give you the base, can you give me the formula for the conjugate acid? All right, and let's again sort of just use an example that we did at the beginning to kind of get our formula down here. We said that ammonia, NH3, plays the role of a base, becoming the ammonium ion, NH4 with a plus. So now we're going to do the exact opposite. What happened to my number of hydrogens? It went up by 1. All right, so we're going to increase number of hydrogens by 1. And what happened to the charge? We accepted that positively charged proton, right? So we're going to increase our charge by 1. All right. So let's do a few more examples here. All right, so I'm going to increase my number of hydrogens by 1. So now I'm at H2SO4. And I'm going to increase my charge by 1, so now it's neutral. Okay. We talked about how water can play the role of an acid. Water can also play the role of a base and accept a proton. All right, so now my formula for my conjugate acid would be H3O, and my charge would increase by 1. So H3O plus. Okay. This ion right here also plays a very outsized role in acid-base chemistry. So we got a fancy name for this one as well. This is what's called a hydronium ion. Okay. All right, so we had sort of said, you know, water, we're not really worried if we spill it on ourselves. Actually, in our second example that we did, this molecule here, acetic acid, this is the main component of vinegar. People ingest vinegar on a daily basis and they're just fine. If you attempted to ingest some hydrochloric acid, you'd be having a bad day, all right? So what is the difference here? Why are some acids so dangerous and corrosive and other ones are just not a big deal at all? They make food a little sour and we love it, all right? The difference is the strength of that acid, okay? We call acids proton donors. That sounds like it's this very nice, neat, gentle, like here, sir, have a proton. No, no, no. Some acids are violent proton donors. They go sticking those things any which way they can find them, right? When you spill acid on your skin, the danger, like a dangerous acid, hydrochloric acid on your skin, the problem is it just starts plugging protons every which way it can, and your body has the correct number of hydrogens, right? It's not trying to have a bunch more dumped on it. So this idea of a proton donor, these strong acids, they are donating those protons violently, all right? So we have this sort of classification of acids where we have some acids that we consider to be strong and other acids that we consider to be weak. Okay, so let's talk about what we mean by strong versus weak acids. A strong acid is one that will completely dissociate in solution. Okay, that's what it means to be a strong acid, is that it will completely dissociate in solution. So what the heck do I mean by that? Let's look at one of our strong acids, hydrochloric acid. If I make a solution with my hydrochloric acid, I'm going to place it in water. Okay? So if this is my acid and this is my base, everybody take a second and predict the products of this reaction. All right, so my conjugate base is that chloride ion. And my conjugate acid, we got a special name for it. What was that name? The hydronium ion. Okay, so what does it mean to be a strong acid? What does it mean to completely dissociate in solution? It means that this reaction here will go 100% to the product side. Will go 100% to completion. Every single one of those HCl molecules that you put into solution will dissociate, will break up into conjugate base, and that proton's going to get donated to whatever that acid is. All right? So what does it mean to completely dissociate in solution? It means that this reaction goes 100% to completion. Okay, so if we look at the equilibrium constant for this reaction, what we call a Ka, because we're talking about an acid, we give it this special little subscript A. But this is the equilibrium constant for this reaction here. If this reaction goes 100% to completion, what do we know about the value of K? Is it a big number or a little number? It's going to be a big number, right? A big number is a reaction that strongly favors that product side. So absolutely, our Ka, our equilibrium constant for these reactions, is a large value. Okay. So then on the flip side, what's a weak acid? It's just the exact opposite. It's an acid that does not completely dissociate in solution. All right, so I'm going to give you an example of a weak acid here. You're just going to trust me that it's a weak acid, and then we'll talk about how we distinguish that here in a second. All right, so it turns out that hydrofluoric acid is considered a weak acid. We're going to do our same chemical equation. We're going to put it in solution. We're going to react it with water. So everybody take a second and give me my products. right, so again, my conjugate acid is that hydronium ion, and my conjugate base is then a fluoride ion, right? Fluorine all by itself with a negative charge. Okay, so again, to be a weak acid, this does not completely dissociate. Okay, so then that means that this reaction does not go to completion. All right, in fact, for weak acids, most of the time, these equilibrium actually favor the reactant side, or very weakly favor the product side. All right, so our equilibrium favors the reactants, or weakly favors the products. Maybe just barely. All right. So, how do I know weak acids from strong acids here? Kind of a good news, bad news situation. You just gotta memorize the strong acids, all right? The good news is that there's 6 of them, okay? There are 6 strong acids that we just gotta know. Everything else we consider to be a weak acid, all right? But we need to know these 6 strong. Flashcard them here. All right, so our strong acids. We got our hydrochloric acid, okay, as well as the larger halogens, what sits under chlorine, hydrobromic acid, HBr, and hydroiodic acid, HI. If there was any amount of whatever the heck AT is, that would probably be a strong acid as well. Okay, we don't really have any of that on Earth. The other 3 are sulfuric acid, H2SO4, pretty much the common go-to strong acid in an organic chemistry lab. The one nobody likes to work with, nitric acid, for whatever reason causes the worst sort of skin irritation out of the lot of them. And then the last one is hydrochlorous acid. All right, so these are 6 strong acids that we just got to know. We got to be able to recognize them as strong acids. Any other acid in the world would be classified as a weak acid. Okay. All right, so we talked a lot about acid strength, all right? There's actually this relationship between acid strength and base strength. So we're going to talk a little bit about that here. Okay? If we look at our strong acid chemical equation here, hydrochloric acid is a strong acid, right? So why is that? It's because its conjugate base, the chloride ion, is super duper stable all by itself. Chlorine is just very stable as an ion. It's more than happy to have that negative charge float around in solution all by itself, okay? Because of that, because it's so super duper stable, as a base, if I'm looking at the reverse reaction, it is trash. It is absolutely a terrible base, the chloride ion. So there's this inverse relationship between acid strength and the strength of its conjugate bases. Very strong acids have complete trash conjugate bases, and weak acids have good bases. Okay, their conjugate bases are good at playing the role of a base. All right, so we have this inverse relationship between acid and base strength. So if we're going to look at acids and their conjugate bases, a strong acid like HCl, right? We classify this as strong. Its conjugate base is so terrible at being a base that we would just say it's neutral. It has no effect as a base. Okay? But if it's not on that list of strong acids, a weak acid, like for example, our hydrofluoric acid, this is a weak acid. Its conjugate base, the fluoride ion, is a pretty decent base. We would classify that as a weak base. All right, so the conjugate of a strong is neutral. The conjugate of a weak is a weak. All right, the conjugate of a weak acid is a weak base. Okay? Because of that, when we move on next week to talking about pH and doing pH calculations, we're going to see that they're super duper straightforward for strong acids. We don't have to worry about what's going on the product side. And then we're going to get to weak acids, and it's going to be a huge algebraic pain in the butt because we got to pay attention to the basicity of what's on the other side of our chemical equation. Okay? All right, and so the last thing we're going to do is look at that Ka expression, our Ka again. Okay, we said that Ka is just an equilibrium constant. We call Ka the acid dissociation constant. And when we're talking about the reaction that corresponds to this equilibrium constant here, it's always the same reaction of taking your acid and reacting it with water, okay? Making a solution with that acid. So you're always going to have this reaction where you have your acid plus water. Right, because water is playing the role of the base, our conjugate acid is always going to be the same, the hydronium ion, and then whatever our conjugate base is. So when we're talking about the Ka of an acid, we're always referring to this specific reaction here of taking that acid and putting it into solution, reacting it with water. Okay? The sort of general form that you'll see for like a generic acid is HA. This is just kind of code for some generic acid. Okay, so if we take that and we react it with water, this would be our Ka expression. Again, we get that conjugate acid, the hydronium ion, and our conjugate base. We're just going to do the same thing we did for our formula before. We're going to decrease our number of hydrogens by 1 and decrease our charge by 1. Right? So HA is for generic acid, A- is for generic conjugate base. Okay, so these values for Ka, they're tabulated in these big books, or now online, or in the back of our textbook in the appendix section, right? You can look up the value of Ka for a particular acid, all right? And again, what do we know about the size of that Ka? A large Ka value, that would correspond to a reaction that favors the product side, right? And a small Ka value would be a reaction that favors the reactant side. So we can sort of judge the strength of a particular acid based on those Ka values, okay? So again, these are tabulated in books and we can look them up. A large Ka value means you have a stronger acid. A small Ka value is a weaker acid. right, and just sort of for example here, HCl has a Ka, and I'm just kind of spitballing off the top of my head here, but it's around 10 to the 5th, maybe even 10 to the 7th. All right, a nice big number that favors our product side. Acetic acid, on the other hand, has a Ka value. It's around 10 to the -5. All right, so a much smaller value that actually favors our reactant side for that weaker acid. Okay, but again, you can look these up in these big tables. You can take two acids, look up their Ka values, and that will allow you to compare their strength. Which one's the stronger acid? Which one's the weaker acid? Okay, if I'm looking for a strong base, then what I'm going to do is look for its conjugate acid and see whichever one is the weakest, right? So a strong base we said has a weak conjugate acid. Right? And since it's a weak conjugate acid, that means that the Ka value for that conjugate base, or for that conjugate acid, is very small. All right? Because again, we have this inverse relationship between acid and base strength. A strong acid has a crap conjugate base. A weak acid, especially a very, very weak acid, will have a very good conjugate base. That's all I got for you. All right, cool. We will pick this up next week. We will start doing some math.